So what that means is when you decrease the when you're immersing your, let's say your cylinder or whatever your system is, into this infinitely large surrounding, firstly the temperature decreases. The temperature decreases at a higher rate at first, and then it slows down to reach the actual temperature of the reservoir. Now, the rate, we assume it's an ideal system, so we assume the rate is going to be constant but exponential. Now, in reality, there will be some differences because you cool down the outside of your system first, and then then there's heat transfer from the inside of your system to the outside, and that's how it works. But we are going to assume it's a constant drop. Now, the entropy is decreasing. The entropy of the system is decreasing. So you're going from the temperature 1 all the way to temperature 2. Temperature 1 was 500 Kelvin, temperature 2 was 300. Now we assume again that we're going to reach that 300. In reality, we'll never reach that because the temperatures will never reach each other because there's no driving force. So remember, the driving force is pushing that temperature difference. Hence the first arrow on that graph. Now, there is no change in temperature for the reservoir, because if you have a coffee cup, you take it outside, it's cooling, but you're not really changing the temperature of the entire world. It's infinitesimal. So we assume the temperature is constant. But you're increasing the entropy of the universe because you're losing heat. Yeah? So you're dissipating this heat into the surroundings. Because as long as the total entropy is positive, so as long as the total entropy is an increase in the entropy of the universe, then this whole system, or equals to 0, it's a feasible process. So if you actually calculate all that, that should equal to each other, equal to 0. Each one will equal to each other, will be equal to 0. Hence, it's a reversible process for the argument's sake. In reality, it's not a reversible process.